Good morning, everyone. I am Gemma Busquet from the University of Barcelona, and I will present a centimeter wavelength survey of the Ophiuchus A cluster at 10 AU resolution. This project is part of the PhD thesis of Isaac Bradley in collaboration with the SKA Cradle of Life Science Working Group. I organized the talk in 3 parts. I will start with the scientific motivation, and then I will introduce you the VLA Ophiuchus A project, and I will conclude with some future prospects for the SKA and ngVLA. So we all know that in order to form planets, dust grains must grow by up to 12 orders of magnitude, from the micro-sized dust grains in the interstellar medium to planetary sizes. This process starts at the very early stages of star formation. For instance, there are evidence of the presence of large millimeter-sized dust grains in the envelope of class 0 protostars. But the bulk of grain growth occurs in the disk. In this context, the synergy of ALMA and VLA observations have shown not only the presence of large grains in the disk, but also variations of the maximum grain size, with low values of the dust emissivity index at the center of the disk. In fact, the dust opacity behavior depends on the wavelength, but also on the maximum grain size. And in order to prove the centimeter-sized particles in disks, we need observations at centimeter wavelengths. The VLA currently operating, and in the future we will have the SKA and the ngVLA. And this is a regime where dust is optically thin. I will now introduce you the VLA Ophiuchus A project, and this is a cluster. This is one of the closest and densest clusters that are host several objects in different evolutionary stages, from class 0 to more evolved class 2 and class 3 young stellar objects. There are previous VLA observations at 3.6 centimeter that detected 16 young stellar objects. The emission or the nature of this emission could not be disentangled, however, because of the lack of multi-wavelength observation. Now, the new project focused in the same field of view, encompassing 18 young stellar objects from class 0 to class 3 YSOs, and we include 3 different frequency bands: the X band, K band, and Q band. I recommend you to check out Isaac's Bradley poster to see the results of the K and Q band observations, and I will focus here on the X band observations. And for this, we did 2 different pointings and with 18 different epochs, reaching a final sensitivity of 4 microjanskis per beam. The goals of this project is to disentangle any thermal or non-thermal ionized gas component, to subtract it and obtain the contribution of thermal dust emission in the disk, and then trace the evolution of the solids across different stages of disk evolution. So this is the summary of the VLA X-band detections. We detected a total of 26 radio sources. 4 are class 0 protostars, 7 class 1 protostars, 7 class 2 young stellar objects, 4 class 3 objects, and additionally we detected 2 galaxy candidates. Here I'm showing some examples of the 3.6 centimeter continuum emission for different kind of objects, for class 0, class 1, class 2, and class 3. Note that the color scale in all panels is the same. And finally, also I show an example of a galaxy candidate in the bottom left part. You can see that most of the emission appears unresolved, even with the most extended configuration of the VLA. So here we really need to push for the next generation of interferometers to allow not to resolve this centimeter continuum emission. And because we have 18 different epochs, we can also investigate the variability of the different sources. Not all sources are variable, and here I show an example of a class 2 object for only some of the epochs, and we can see that there is a huge increase on the peak intensity for one of the epochs, by a factor of more than 10, and presenting a variability of a 94%. Collecting the data from ALMA 3 mm, 1 mm, and also previous VLA observations at 6 centimeters, we can now build a spectral energy distribution for all our objects. Here I'm just showing a couple of examples. This first example is for a class 0 protostar, and we can fit the spectral energy distribution with a combination of two power laws and disentangle the contribution from free emission and from dust thermal emission. So in green, I'm showing the free contribution, and in orange is the dust thermal emission. In this case, we can see a very steep a slope indicating the presence of small grains in this class 0 object. In the next example, this is a class 1 source. The spectral energy distribution is different. Again, in green is the free contribution, and in orange, the millimeter dust thermal emission. So we can see that in that case, the spectral index is about 2, which indicates that in this class 1 object, the grains are bigger compared to the previous example. So this is still work in progress, and of course, we can investigate how this spectral index changes along the evolutionary stages in our sample. I will now conclude this talk with some future prospects, and in particular, I will start with the Ophiuchus cluster. This actually, our VLA observations, it's a precursor or a pilot for the future SKA mid key science project of a very deep integration in this Ophiuchus A cluster. It's about 1,000 hours, reaching a resolution of about 5 astronomical units, and this resolution will actually allow us to resolve the different structures in the disk and investigate the variations on the dust grain sizes along the disks. The second example is to go beyond the solar neighborhood and extend these kind of studies to more distant regions. And for this, I'm showing here an example. This is a pilot project that was conducted towards this infrared dark cloud. This is G14.2, located at 1.5 kiloparsecs. And the point that I want to make here is that to reach a sensitivity comparable to the surveys in the solar neighborhood, we needed about 11 hours per pointing. So this is something that for the VLA, it's highly time consuming, but for the next generation of interferometers, we can reach similar sensitivity in only 1 hour of observing time. And for this, I want also to point to Elena Diaz Marquez poster. If you want to find out more about this project, you can go and see her poster. Finally, I want also to introduce you the VLA Orion A Large Survey, VOLS. This is a VLA large program that was that started observation last year, and this is part of a large collaboration involving several people, and we are mapping the northern part of Orion A in 2 different frequencies at the C-band and Ku band with the A and B configuration, and not only in the continuum, but also in spectral lines, including radio recombination lines and maser emission, and also in polarization mode. So you can also go and see Josep Miquel Girard's poster to find out more about the BOLS project. Well, thank you very much for your attention, and I will be happy to take questions in the Slack.
Okay, questions from the audience for Gemma? So I do have a question, Gemma. You were pointing out the variability of the sources in X-band. So I didn't notice how big in amplitude it was, the variability, but are you concerned about the effects that may have on the measurement of the SED? Meaning your SED may be changing, you measure points at different times, etc.
Yeah, well, hello, good morning. Yeah, the sound is not good. Even now, I mean, I can understand you more or less, but the sound is awful. Yeah, I'm concerned about the variability. I mean, we have several objects, especially class 2 objects that show a huge variability along the different wavelengths. And of course, the spectral energy distribution will not be easy to deal with this. I mean, because we have epochs that it's a simultaneous observations in both X, Q, and K band, then we can not try to build this SED with only one of the epochs, no, that it's more or less simultaneous to the other wavelengths. So this will be, you know, the way, you know, to address the SED.
Thank you. Questions in the room? We have to distribute more coffee, clearly. Okay,
Thank you for your nice talk. I'm from York University, and you showed us the image-based comparison between the young stellar objects and the extragalactic objects in centimeter wavelengths. And sometimes the SED of protostars and extragalactic objects shows quite similar to each other, so it's very hard to distinguish between these two classes. So how do you clearly discriminate the extragalactic object from the real protostars? Could you tell us?
Yeah, well, here is just, if I understood correctly, the question, because the sound is not good, but they are galaxy candidates according to the SIMBAT database. So this is something to know to check in more detail, but it's just what it comes from the database itself. The other objects are also observed at other wavelengths and are well-known young stellar objects. So there are only 2 radio sources that, in principle, are classified as extragalactic sources. But yeah, we can also check with our data.
Good. And there is a question in Slack here. Can you repeat it for everybody?
Sure. So Michael Rubin asks, are your ionized gas measurements interesting or only the dust? I'm interested in the spectral index differences at centimeter wavelengths, for instance.
Yeah, well, we are interested in both. I mean, the dust thermal emission for the grain growth studies, but also the ionized gas, to look for any possible thermal radio jet, and also for class 2, class 3 objects, if probably they are associated with non-thermal emission, from active magnetosphere or synchrotron emission. So we are interested in both the the thermal emission and the non-thermal emission.
Good. Any last question from the audience? Tyler is advancing very slowly in this direction.
So we're just going to pause before the next video while the tech guys sort it out. So the Zoom is sounding really terrible online.
Okay, so Gemma, what the message was that the sound is indeed really terrible for you.
Yeah. Okay.
So they are going to try
But
to fix it.
you can understand me or you can hear me well.
Yeah, your sound is perfect.
Okay. I think the problem is on Zoom because I cannot. I mean, the sound it's yeah, it's super bad here.
Okay. You still have time for another question if somebody wants to break one. Okay. Well, it seems that we're going just to wait for the technical problems to be solved. So thank you very much. Emma, let's thank the speaker.
Thank you.